Okay, good morning. So this is our third lecture. Now, yesterday I have shown you a number of properties. Okay, so if you exactly remember, then something about 9 properties of a fluid I have mentioned. Now today we will try to see one by one in bit detail. Okay, so some of the properties I will just introduce because these have more specific detailing in the course of thermodynamics. However, the properties which are very much relevant to this particular course of fluid mechanics, these I will try to discuss in more detail. Okay. So, say first we were talking about the property. We can start with any. So, say we talk about density. Okay. So, typically, density of a fluid is defined as the ratio of mass per unit volume. Okay, so that is the standard definition of density. Now, as it is mass per unit volume, like m by v, so its unit will be, mass is having unit kg and volume is having unit meter cube. So in SI units, SI system of units, the unit of density is nothing but kg per meter cube. Okay, so this is very generic definition of the density. Typically, density is represented by symbol rho. So rho equal to m by v. Okay. However, if we try to introduce the concept of continuum into the definition of density, then we have to put one more thing over here. Okay. So why I just wanted to introduce the concept of continuum, because in this expression of mass per unit volume, we never specified that what should be the size of our volume while we are estimating the density. Okay, whether the volume which we are considering, it should be of the order of this room, or it should be of the order of this size equivalent to that of a chair, or say size equivalent to that of your eraser, or even more smaller. Okay, so when what should be the appropriate size of the volume corresponding to which we are actually calculating the density. So this is something which can be explained with the help of the concept of continuum. So let's consider that we have a large container, and in this large container we are having some fluid. Okay, so as we will be having some fluid, so obviously we will be having arbitrary number of molecules moving here and there. Okay, and of course in between these molecules there will be some void spaces. Okay, now in this room, so there can be multiple consideration. So let me do that. So first thing what I can do, I can take a control volume which is of size something like this. Okay, then say if this size control volume I move to any location, it will almost enclose the same number of molecules within it. Okay, so if it is enclosing the same number of molecules within it, then mass in this particular volume will remain almost the same. Is this one clear? Okay, on contrary, if I take say some volume only like this, then what will happen? Say here it is enclosing 2, there can be some portion where it is not even enclosing a single molecule. Okay, so it means that whenever we are deciding our control volume, okay, so if the size of this volume is very small, then we can have certain situations where this volume is coinciding with the molecule, so it is giving a certain amount of mass and certain volume. So when it is having certain amount of mass and certain volume, it will give us some finite value of density. On contrary, if it is say projected on certain portion where there is no molecule, then our mass will be 0, so it will give us the value of density as 0. On contrary, if I increase the size of the control volume in such a way so that if I fix this control volume at any location within the room, or if I consider this control volume at any point of time, okay, so this also can happen that this control volume, say I am counting the number of molecule at time t1 in order to calculate the mass. I can also count at some other time t2. Okay, so at other time t2 also, if our system is not changing, then also our control volume should enclose same number of molecules. Okay, so that is something what we have to do. We have to choose our volume actually very precisely, and our volume what we are selecting for finding out the mass for estimation of density, that should satisfy the limit of continuum. Okay, so what I will do over here, I will plot delta m by delta v. So now I am not talking about any large finite volume, rather I am talking about some elemental volume delta v, and within that elemental volume delta v, say my mass is delta m. Okay, and mass is nothing but the sum of masses of individual molecules which are accumulated inside that volume. Okay, so now if I plot this as function of delta v, so what is the meaning? The meaning is that this delta v means this this is nothing but the size of the control volume. So on the left side, size is small, and as we are moving towards the right, size is actually increasing. Okay, so in this situation you will be finding that up to certain region my curve of density will keep on oscillating. I will not get a definite value. It will keep on oscillating, and after reaching a certain value of the volume, this curve will become almost a fixed quantity. Okay, so I can say that the point where these oscillations are stopping, this is some delta V star volume above which only our continuum approach will be fully satisfied. Is this point clear? So if I take any volume which is less than delta V star, then my approach of continuum will not be satisfied. Okay, so that is the reason when I define density, I put one limit over here. I will be writing mathematically delta m by delta v, but subjected to the condition that my delta v should be greater than delta v star. Okay, because if delta v becomes less than delta v star, then at different times or at different locations within the control volume, we cannot satisfy the same number of molecules present. Okay, so it means effects of voids is coming into consideration. Okay, so it means our continuum is not satisfied, and we will not be able to define the true value of density which should be applicable for a continuum. Is this point clear? So this is density is very important property. Now the reciprocal of density is something which is called as specific volume. So specific volume is typically represented with symbol small v, and that is equal to nothing but delta v by delta m. So any thermodynamic property you have, say its energy, internal energy, enthalpy, if you divide it with mass, then we call that quantity as nothing but the specific property. For example, here I am dividing volume with mass, so it is called as specific volume. Similarly, if you divide internal energy with mass, it will be calling specific internal energy. The benefit is that if we divide any property with mass, if any extensive property I divide with mass, it becomes specific property, and all the specific properties are nothing but of intensive nature. Means this does not depend upon the quantity, because quantity you have already taken in the per unit quantity. Okay, is this one clear? So all the specific properties, you will be studying this in detail in your subject of thermodynamics, but just I introduced over here because specific volume is the term which many times we will be referring in this subject. Okay, so specific volume is nothing but 1 by density. That is the reason its unit will be meter cube by kg in SI system of units. Okay, now when we define density, typically density is also represented in terms of, particularly for fluids, in terms of one more another parameter which is typically called as specific gravity. So can you tell me what is specific gravity? Sg, that is equal to density of liquid divided by density of reference liquid. Okay, so for typically for liquids, reference liquid is water. So density of water, and this is taken at 4 degrees Celsius. Okay, so that is nothing but the definition of specific gravity. For example, our liquid mercury. So if I have to write down the specific gravity of liquid mercury, that will be equal to density of mercury is how much? 13,600. If you have to go precisely, 13,580 divided by density of water at 100 degrees Celsius is 1000. So we will be getting value as 13.6. As it is the ratio of same quantity, so it is nothing but dimensionless. Okay. So specific gravity till now, what I have done, I have defined it for liquids. What about gases? Okay. So for gases, specific gravity of gas, let me write this liquid. Specific gravity of gas is typically written as density of the gas divided by density of, for gas reference fluid is nothing but air, density of air at what conditions? Standard temperature pressure conditions. So typically standard pressure is 1 atmospheric and temperature is 25 degree Celsius, 20 or 25 degree Celsius. So now at this point air is having density close to 1.205 kg per meter. Okay, is this point clear? Now whenever we talk about the density actually is a important property and it strongly changes with changes in pressure and temperature. So typically for liquids, density changes very strongly with changes in temperature, but with changes in pressure, density does not change much for liquids. On contrary, for gases, pressure is having more significant effect on the density in comparison to the temperature. Okay, so if we have to find this effect, so we have some quantities with the help of which we can define this. So very important quantity which we use, that is called as coefficient of compressibility. Okay, this is also known as bulk modulus of elasticity, or it is even also called as bulk modulus of compressibility. Okay, so basically bulk modulus of compressibility is say given by symbol kappa. It is equal to minus delta P divided by delta V by V. Okay, so that is our nothing but the coefficient of compressibility. So I can simply write it as minus of V times, let me write this V over here in specific terms. So if I write in specific term, then it will be specific volume small v over here. Okay, so minus small v del P upon del V. Now when we define this coefficient of compressibility, it can be defined either at constant temperature or at constant entropy. Okay, so coefficient of compressibility, this is the generic definition, but this generic definition is applicable for two situations, either for constant temperature or for constant entropy. So whenever it is defined for constant temperature condition, because See, here in this coefficient of compressibility, I am only accounting for changes in volume when I am changing the pressure. So if I am doing so, I have to maintain some other property as a constant, because if I parallelly vary other property also, then its effect will also come into picture, and I will not be getting the true reflection whether this effect is only contributed due to pressure or any other parameter. So that is the reason while we do perform this, we try to maintain either temperature constant or entropy constant. So for our fluid mechanics applications, because majority of the time if heat transfer is not involved, our temperature of the fluid remain the constant. So that is the reason for fluid mechanics problems we define it at constant temperature, and typically we also call it as isothermal coefficient of compressibility. Okay. On contrary, if you go to compressible flow applications, okay, so in case of compressible flow applications, when there are changes in the density or in the pressure, there are significant changes in the temperature as well. Okay, so particularly if you talk about gas dynamics and this aircraft, flow over aircraft. Okay, so that comes under the subject of compressible flow. So there actually temperature does not remain the constant, and particularly for compressible flow analysis we can define the isentropic compressibility. Okay, so over here what we will be doing, we will be considering temperature is equal to constant. Okay, is this one clear? Now we know that specific volume is nothing but equal to 1 by density. Okay, so can you calculate del V? Del V will become, what you will be finding over here? Tell me. This will be del of U by V. So U will be 0 minus del of rho divided by rho square. Fine. So del V can be written as minus del rho by rho square. Let's substitute this definition over here. So if I do so, then my kappa will become minus of this specific volume, I will try to write as 1 by density times del P by del rho, and I will be getting a constant multiplier as minus of rho square. Fine. Is this one clear? Is this one clear? So for isothermal and adiabatic conditions are different. Even if you are having a heat transfer situation, and if you are adding heat to a system and you are rejecting the heat out of the system at the same rate in terms of work or heat transfer only, then also temperature will remain constant. So for isothermal condition to maintain, always it has to be adiabatic. It is not at all required. Okay. No, I don't want to do over here entropy. Isentropic condition will be where you have, there are, once again for isentropic also there are multiple conditions. Okay, so maybe let's not discuss, after the class you can discuss that in more detail, or in your subject of thermodynamics also that will be coming in detail. Okay, because that is slightly different. So from here what you will be getting, you will be getting that this coefficient of compressibility is equal to density times del P by del rho at constant temperature. Okay. So if you see, one important thing, whenever I have written the generic definition in terms of volume, then what I have mentioned, I mentioned over here that del V by del V. So the reason for negative sign outside is that when I will be actually increasing the pressure, so increase in pressure will result in decrease of specific volume. So that's why this delta V will become negative if delta P is positive. So in order to keep the quantity, overall quantity as positive, we are writing it as minus del P by del V. Minus sign outside. Okay. Is this point clear? On contrary, in case of density, automatically you are seeing that it is coming as positive, because if you are increasing the pressure, then volume is decreasing but density is increasing. So this delta P will also be positive. Okay. Now this is something which I have written in the form of differential equation. If I have to write for finite change, say in a system I am changing the pressure by some finite amount delta V, my volume is specific volume is changing by finite amount delta V, and my say volume was V. So in that case, if I consider particularly the case of a water, in case of water, say if water is initially at 1 atmospheric condition, if I have to change the density or the volume of water by 1%, okay, then I need to change the pressure. I need to go to new pressure, that is nothing but 210 atmosphere. Okay, so it means in order to change the density of water just by 1%, you have to change its pressure 210 times. You have to increase the pressure 210 times. Typically, if you see other thing, that this coefficient of compressibility, denominator term is actually the ratio of same quantities, so it will be dimensionless, only it is having dimension of the pressure. As it is only having the dimension of the pressure, so its unit will be unit of pressure. Say in SI units it will be fine. Is this one clear? Are you able to understand this? Okay, so for water I told that it will be something about 210 atmospheric. So I can say that the compressibility of water under atmospheric conditions, okay, is nothing but, this is at atmospheric temperature and pressure conditions, is nothing but delta P has become, so yeah, I can write it in terms of, for finite change, delta P by delta V minus V into delta P by delta V. Okay, so this is something which is minus delta P into delta V by V. Now delta V by V is nothing but 1%. That is something which I have called 1%. So 1% I can write in the denominator 0.01, and in the numerator for this 1% change my delta P has to be 210. Okay, so corresponding to this I will be getting the, say this is -1, so I will be getting the value as 21,000 atmospheric. Now 1 atmospheric is equal to 101.325 kilopascals. So typically I can say that the compressibility of water at atmospheric conditions is nothing but something about 210 into 10 to power 5 pascals, sorry, kilopascals. Fine. Is this point clear? Yes, yes, yes. So this is kind of, say, very small change. Yeah, so approximately 200. Okay. Is this point clear? So this is the compressibility of, coefficient of compressibility of water. So it is a very, very high value. Okay. So typically if I talk about the gases, then for gases, one very, very important equation at atmospheric condition which is applicable, that is nothing but ideal gas equation. Okay. So as per ideal gas equation, I can write that P is equal to rho RT. Okay, where rho is density, R is characteristic gas constant, and T is temperature in absolute scale. Okay, so typically, as I have shown you the definition of coefficient of compressibility as density times del P by del rho at constant temperature. So what I can do from this ideal gas equation, I can calculate del P by del rho. So del P by del rho will be nothing but RT, and RT can be written as P by rho. Fine. So now if I substitute it over here, then into P by rho, so this is coming equal to pressure. So for ideal gas, I can say for ideal gas compressibility is nothing but equal to the pressure. Okay. So at atmospheric pressure condition, if you consider air to be an ideal gas, then you can see the compressibility of air is nothing but equal to 1 atmosphere. On contrary, the compressibility of water is 210 atmosphere. So you can see now how large pressure is needed for changing the density of liquid when we are changing pressure. On contrary, if I have to change the density of gas, then it can be easily changed. Fine, because its coefficient of compressibility is very less. Okay, so another term which is very important, that is called as isothermal compressibility. Isothermal compressibility is given by symbol alpha, and it is nothing but 1 by coefficient of compressibility. So typically for an ideal gas, alpha for ideal gas will become 1 by pressure. Fine. Is this one clear? And in general, if you have to define alpha, then it will become 1 by rho into del rho by del P at constant temperature. So that is the generic definition of this alpha. Is it clear? Any doubt till this point? Likewise, we have coefficient of volume expansion. So what does coefficient of volume expansion give? It is given by symbol beta. So it will tell us how our volume is actually changing with temperature at constant pressure conditions. Okay. So typically I can write it as del V by del T, del V by del T, and this will be 1 by V at constant pressure. Now you can see that I am not putting any negative sign over here. Why I am not putting negative sign? Because when you increase the temperature, then volume also increases. Okay, so both behave in a similar direction. As both are behaving in similar direction, so I am not putting negative sign. Okay. So now if I once again put the definition of specific volume as 1 by density over here, so I will get this as nothing but 1 by rho into del rho by del T at constant pressure. That is nothing but the isobaric condition. Okay. Is it clear up to this point? Okay, so once again, let's try to see this definition for an ideal gas. And from here also you can see that this rho unit will cancel out. So typically it is having the units of 1 by temperature scale. So it will be 1 by Kelvin. Okay. Fine. Unit will be 1 by Kelvin. Now, if I talk about over here, its value for an ideal gas, then what I will be getting? For ideal gas, once again, P is equal to rho RT. From here, rho will become P by RT. Okay. Now you do calculate del rho by del T. Tell me what will be del rho by del T at constant pressure. What will be del rho by del T? Pressure is constant, R is constant, characteristic gas constant, that is also constant. So P by R is constant. What is the derivative of 1 by T? Sorry, one mistake I did. when I am changing from volume to density, then I must put a negative sign over here. Mathematically also that will be coming, because temperature and density behaves in a dissimilar fashion. Okay, so in opposite direction. Okay, what will be P by R? Times minus 1 by T square. Fine. So 1 P by RT will be becoming rho, so I can write it as minus rho by T. Is this one clear? Can I write it minus rho by T? Okay, so now let's substitute this. So beta for ideal gas will become now minus of 1 by rho times minus of rho by T, which is nothing but equal to 1 by T. Okay, so if you take temperature in absolute scale, because ideal gas equation is applicable only in, here temperature has to be in the absolute scale. So it means temperature value must be in Kelvin. So that's why I must write over here it is in Kelvin. So unit of beta will become 1 by. Fine. Any doubt up to this point? Now, the thing is, in your system, you may have the combined effect of temperature and pressure in certain cases. So what I can do for combined effect, mathematically I can define that, say my specific volume is function of both temperature and pressure. So in that situation I can write del V as nothing but equal to del V by del T at constant pressure into dt plus del V by del P at constant temperature into dP. So that is from the definition of the total derivative. Okay. So now try to replace these quantities in terms of what will be del V by del T at P? Beta times specific volume into dt. Okay. And what will be del V by del P? Minus alpha times specific volume into dP. So ultimately I will get beta dt minus alpha dP times specific volume. So ultimately I can write that del V by V is nothing but equal to beta times dt minus alpha times dP. So fractional change in specific volume is equal to beta times change in temperature and alpha times change in pressure. Fine. And in terms of finite changes, so this is for infinitesimally small change. If I have a finite change of the quantity, then I can write delta V by V is nothing but equal to beta times delta T minus alpha times delta V. Clear? Up to this point, is it clear? Okay, to this there is one more connected topic. So because till now we are only talking about density. Okay, and to explain the variation of density with temperature and pressure, we had to study the concept of coefficient of compressibility and coefficient of volume expansion. Okay, now there is one more connected topic, and that is under what scenarios of fluid mechanics we can consider that fluid is incompressible, like there is no change in its density, or say negligible change in its density, because no change is not at all possible, there will be certain change. On contrary, what are the scenarios where we will be having significant changes in the density, and there considering the incompressible assumption is not at all applicable. Okay, so let's try to understand that part. So how we can understand that is, let's consider that I have a piston cylinder system. So this is a cylinder wall, and this is a piston over here. And this piston is sliding in the rightward direction with some velocity dv bar. So v I am using say symbol for volume, so for velocity say I am using v bar. Okay, so with infinitesimally small velocity dv bar, it is moving towards the right. Say initially it was having some stagnant gas. Okay, now so obviously we will be having some gas molecules almost uniformly spaced over here. Okay, so order may be random, but spacing will be almost kind of. Now what is happening, say typically this gas was at density rho, its internal energy was U, its enthalpy was H. What is internal energy, enthalpy? These concepts also I will be explaining, but first I thought let me explain the connecting concept. Okay, so we are considering that initially till the piston was stationary, the density of this was rho, internal energy was U, and enthalpy was H. Okay, now what I have done, I have say given very small motion to this. When I have given very small motion to this, what will happen? The molecules which are just adjacent to the piston, these will get kind of compressed. Okay, as these are getting compressed, these will reach a state of slightly higher energy. Okay, it means their pressure will be slightly higher than the, say here if pressure is P, then their pressure will become slightly higher than that. So it means say P plus dP, because I am moving piston with very small velocity. Okay, so pressure will become P plus dP. Similarly, internal energy will become U plus du, enthalpy will become H plus dH. Okay, and let's consider that in this particular zone, if I have the fluid, then say speed of sound in this medium was C. So when I am slightly compressing the molecules, then what will happen? Speed of sound in these molecules will also increase. So you know that speed of sound in solids where molecules are closely spaced is more in comparison to liquids, and then it is least in case of gases. Okay, so what I am trying to say is that near the piston I have slightly compressed the molecules. Okay, so as molecules has become slightly compressed, so here speed of sound will also become C plus dc, slightly larger than the speed of sound in the other way. Okay, now though piston is moving at its own speed, which is dv bar, but the molecules which are over here, in these molecules they are having speed of sound as C plus dc. So of course what will be happening, this information, whether a piston is pushing the molecules from the back, this molecule will translate this information to next molecule at the speed of sound. Okay, why? Because sound is nothing but a pressure wave. Okay, so whenever we speak, what I am doing, when you speak, if you just place your hand very close to in front of your mouth, so you will be finding that some pressure is coming on your hand. Okay, so typically sound is also nothing but a pressure wave. So what I am doing is actually I am pressurizing the molecules which are just adjacent to me, and these molecules then are transferring that information to you. Okay, is this point clear? So that is nothing but a sound wave. The best part is that unless or until you are creating some huge explosion to create the sound, across the sound wave pressure change is very small. Okay, so source of sound wave is here, and when I am speaking, so in this zone pressure will be slightly larger, but in the other end pressure is small. But this, when the sound wave is traveling, it is actually increasing the pressure of these molecules, and then these molecules are further passing that information to the next set of molecules. Okay, so what I am trying to say is that sound is nothing but a pressure wave, but it's a weak pressure wave, because when it travels, it changes the pressure of molecules by a very small amount. Okay, so that is something which I am trying to say over here, is that whenever these immediately adjacent molecules will feel that something is pushing them from the back, so these molecules will pass this information forward. But when these will be passing this information forward, obviously this is nothing but a situation equivalent to that of a sound wave, so these will be passing the information at the speed of sound. Okay, so whatever the wave front will be moving, that will be moving something like this very fast. Okay, so I can consider that, say, at some instant the wave front is at this location. So when the wave front is moving, before the wave front my properties will be P plus dP, C plus dC, U plus dV, and C plus and H plus dH. On contrary, on the other side my properties will be, because till now wave front has not reached to that location. So if it is not reached to that location, so their properties will be nothing but the free stream properties. Is this point clear? So now what I will be doing, I will consider that I have fixed a control volume over this wavefront. Okay, and let's consider that this control volume is moving with the wavefront. As the wavefront is moving, so control volume is also moving. Is this point clear? So now what I will do, I will draw this control volume over here. So this is the control volume, and this control volume is nothing but drawn across this wave front. Okay, so for this control volume, if I consider, then on the right side density will be rho, and on the left side where wave has already passed, their density will be rho plus d rho. Enthalpy will be H plus dH. On contrary, here enthalpy will be H. Okay, now let's consider that I have fixed the observer on the control volume, and observer is also moving with the wavefront. So when observer is also moving with the wavefront, what will happen? Observer will feel that this fluid, which is kind of stationary over here, because wavefront is moving with speed of sound c, so this will feel that it is coming towards the wavefront at velocity c. Is this point clear? If you have still air over there and you are moving towards that air with velocity c, and if you put the observer, you are in, yourself as the observer, then what will be happening? You will be feeling that air is coming towards you with velocity c, the velocity with which you are moving. Okay, so typically when you are sitting in a car, you see that other objects which are in the surrounding, these are coming towards you with the same velocity. So that is something which I am saying. So we will be feeling over here that the air which is in front of the wavefront, that is approaching to us with velocity c. On contrary, from this side we are moving away, so here we will be finding that air is moving away from us with velocity c, because wavefront is moving with velocity c. On contrary, this piston is also coming with some velocity dv bar. Okay, so what I will be feeling, this piston is also pushing the air towards the right, so the relative velocity which we will be feeling is c minus dv bar. Is this one clear? Is this clear? Because we are moving away from c, but with dv bar, that air is also coming towards us, so relative velocity between the observer and the air which is moving towards the right, that is nothing but c minus dv bar. Fine. Now it is very easy. So over here I have already defined all the symbols in yesterday's lecture, but once again if I repeat, then rho is density, h is enthalpy, c is speed of sound. Okay, so now if I write mass conservation across this control volume, so we know that for mass conservation, though we will be deriving it in this subject, but at the moment if we consider that we know for one dimensional system, don't use mobile phone. So as I have already in the subject of thermodynamics or your basic schooling, you study that I can write rho into area into velocity as nothing but equal to mass flow rate. Okay. So by applying the conservation of mass, that mass flow rate at left face of control volume is equal to mass flow rate at right face of control volume, I can call that rho times rho plus d rho times C minus dV bar will be equal to rho times C, considering that area of right and left faces are same. Okay, is this point clear? So now you try to simplify this equation. What you will be getting? Rho C plus, sorry, rho C minus rho dV bar plus d rho C minus d rho dV bar equal to rho C. So rho C will cancel, and once again, because these quantities d rho and dV bar infinitesimally small, so their multiplication will also be negligible. So this will be negligible. So ultimately what I will be getting is that d rho into C times d rho minus rho times dV bar is equal to 0. Is this point clear? Similarly, if I apply the energy balance across the control volume, then what will be happening? Energy on left side of the control volume must be equal to energy on right side of control volume. So the energy will be nothing but, this is a flowing stream. So energy for flowing stream becomes nothing but enthalpy plus kinetic energy. Kinetic energy will be C minus dV bar square by 2, and sorry, this will be on the left side, it will be H plus dH. And here it will be H plus C square by 2. Consider that there is no changes in the potential. Okay. Is this point clear? So try to simplify this. What you will be getting? It will be H plus dH plus C square by 2 plus dV bar square by 2 minus 2C dV bar by 2 equal to H plus C square by 2. So C square by 2 and H are cancelling out. dV square will be negligible. So ultimately from here I will get that dH minus C into dV bar equal to 0. Is this one clear? So say this is my equation number 1. This is equation number 2. Now typically the process of propagation of sound wave is nothing but an isentropic process. Okay, so how it is isentropic? Because if you see across the sound wave we are not adding any heat. So when sound wave front is moving, we are not adding any heat. So it means it is adiabatic. On contrary, across the sound wave front, the changes in properties are very, very small. So pressure is changing by amount P plus dP, enthalpy is changing by amount H plus dH, temperature is changing by amount T plus dt. So across the sound wave, the property values are having difference, very small difference, that is infinitesimally small difference. So if infinitesimally small difference is there, it means properties on both the sides are almost the same. If both the sides properties are almost the same, then process can be called as a reversible process. Okay, so if process is both adiabatic and reversible, then it will be nothing but an isentropic process. Okay, now your question is clear. So typically across sound wave we are not adding any heat, not removing any heat. Moreover, the change of properties across the sound wave front are very, very small, because sound wave is nothing but a weak wave. Okay, so that is the reason that I can call the propagation of sound wave as nothing but isentropic process, because it is both adiabatic and reversible. Okay, so now we know, that is, once again you will be studying in thermodynamics. So from thermodynamics, one property relation we know, that TdS is equal to dH minus dP by rho. So that I am directly writing over here, because it is coming from the subject of thermodynamics. In thermodynamics you will be studying this relation in detail. Okay, so now for isentropic process, ds will be equal to 0. So from here dH will become nothing but dP by rho. Okay, so from this equation number 3, now I can go back into equation number 2 and I can substitute this value. So if I substitute, then I will get equation 2 as dP by rho minus, or dP by rho is simply equal to nothing but C into dV bar. Okay, is this one clear? dP by rho has become C into dV bar. Now one another thing, you have C into, say, dV bar you have in equation number 1. So from equation number 1, dV bar you can write C d rho by rho. What will be value of dV bar? C d rho by rho. So this value of dV bar from equation 1, I will be now substituting down. So this C d rho by rho, please let me know the value. So dP by rho is nothing but equal to C times, in place of dV bar what I will be writing? C times d rho by rho. So rho is getting cancelled. From here you can see that speed of sound in a medium C square can be written as del P by del rho at constant entropy. Why I am writing constant entropy? Because just now I have used a relation TdS equal to dH minus dP by rho, and through this relation I am able to calculate this. Okay, so if I write, so speed of sound in any medium is nothing but equal to del P by del rho. So it means that, what is del P by del rho? Now you can write this in terms of compressibility. Okay, so though compressibility, here I have defined isothermal compressibility, in the similar way we also have compressibility as nothing but the isoentropic compressibility. Okay, so isentropic compressibility is defined as 1 by rho times del P by del rho at constant entropy. So what I can call, I can say that my speed of sound in any medium is nothing but equal to isentropic compressibility times rho. Is this one clear? So it will be becoming nothing but equal to rho times isentropic compressibility. Okay, so this is another relation for the speed of sound. Is this one clear? So now we will stop at this point, and further inferences of this concept, that how speed of sound helps us in defining the incompressible or compressible flow, that we will study in the next lecture.